In this video, we are going to talk about sigma notation. And so sigma notation is just kind of a shorthand that we're going to be using quite a bit throughout the remainder of Calculus 1. And so the way the notation goes is you write this Greek symbol called sigma. Below it you write some I equals m to some value n. And then we have something a sub I here. And I'm going to explain each piece of this. So now what this actually means is this literally means take a sub m plus a sub m plus 1 and so on to a sub n, where each of these a sub I, so a sub m plus 1 and so on to a sub n, are some known values. So it's basically just telling us to add up a bunch of things. And now the way you interpret this notation is this piece at the bottom tells us where to start. So it tells us to start at m, and this piece here tells us to end at n. The a sub I is telling us this is what we're adding up. And then the sigma literally just means add things up. Okay, so that is what sigma notation is. Typically, our a sub I are going to come from a function. So typically, we're going to have something more of the form, the sum from I equals 1, or m, to n of f of I, which would then say we do f of m plus f of m plus 1, and so on to f of n. And so that's the typical way we're going to be doing it. Usually we'll have a function, but if you just have a list of numbers, a sub I, you can do the same thing. And in Calculus 2, you'll see that you do just have a list of numbers sometimes when we're doing this. But we're always going to have a function in our situation. And so let's look at some examples of this just to make it a bit more clear. And so if I write down something like the sum from I equals 1 to 4 of I squared, this is saying 1 squared plus 2 squared plus 3 squared plus 4 squared, which is equal to 30 if you actually compute it. And so all it's telling us is to do 1 squared plus 2 squared plus 3 squared plus 4 squared. Next, if we write the sum from I equals 3 to n of I, this is saying do 3 plus 4 plus 5 plus 6, and so on up to n. Now we don't know what n is, but it's typical that we will go to some arbitrary value. We won't usually have like an ending point in mind, we'll just have some arbitrary value in mind. And then just one more example to make this a bit more clear. If we take the sum from j, and so I'm going to use j instead of I this time, just to denote that we can use other letters. So from j equals 0 to 5 of 2 to the j. This means 2 to the 0 plus 2 to the 1 plus 2 squared plus 2 cubed plus 2 to the 4th plus 2 to the 5th. And if you add those all up, you get 63. Okay, and so that is the idea behind sigma notation. Now, sometimes we'll have a summation and want to go backwards. And so for the next example, we want to write the summation 2 cubed plus 3 cubed plus 4 cubed up to n cubed in sigma notation. Okay, so we just want to take the sum that we've written down and we want to write it down in sigma notation. And so notice we're just adding things up. We seem to be starting at 2 and ending at n. And so a natural thing to say is, well, we'd have the sum from I equals 2 to n, because we started at 2 plugged into our formula, ended at n, and the formula we're plugging it into is the cubing formula. And so this is the sum from I equals 2 to n of I cubed, because each time we're cubing something and then adding it together. And so, like I'm saying, each of these is getting plugged into the function f of x equals x cubed, and then I'm just adding all of the pieces together. Now, sigma notation is not unique, so we could have written this as the sum from j equals 1 to n minus 1 of j plus 1 cubed. If you plug things into this, you'll see you get out the same summation. There is nothing specifically special about the one we pick. You just have to pick one. Usually we pick the one that is kind of the simplest in appearance, and so that would be this one. But both of these are valid summations. There's not just one way of doing it. So one more example, or a few more examples. If we did something like the square root of 3 plus the square root of 4 plus the square root of 5 plus the square root of 6 plus the square root of 7, well, if I'm adding all of these up, notice I'm taking the square root of each term, and I went from 3 to 7. So this would be the sum from I equals 3 to 7 of the square root of I. Next, we could have something like 2 plus 4 plus 6 plus 8, and so on to 2 times n. Notice here that I've got the evens here, so I'm doing 2 plus 4 plus 6 plus 8 up to 2 to the n. And so here, the ending thing is what's giving us the idea. If we want to end on 2 times n, and we're only adding evens. And so we could write this as the sum of 2 times I, which will get the evens. And we know we want to end at n, because the last term is 2 times n. And we want to start with 2. Well, that means we're starting with I equals 1, because 2 times 1 is 2. And so that gives us our summation of 2 plus 4 plus 6 plus 8 to 2 to the n. Okay, now there are a few properties to be aware of when it comes to summations. And so these are called the summation properties. And so we're going to assume C is a constant. Now all that means is it does not depend on I. So this is just like in derivatives, like if we have 2 times x, the 2 is kind of unaffected by taking the derivative of 2 times x. You just pull it out. We're going to see basically the same thing happens here. And so if we take the sum from I equals m to n of c times ai, this equals c times the sum from I equals m to n of a sub I. Now all we're doing here is the distributive property. We're just saying that instead of, this is like the distributed out form, so this is like CAM plus CAM plus 1, and so on to CAM. All we're doing is we're just pulling the C out in front of everything, adding all the things, all the AIs up, and then multiplying by C. So we're kind of undistributing in this property. So the second one that we have is the sum from I equals m to n of a sub I plus b sub I is equal to the sum from I equals m to n of a sub I plus the sum from I equals m to n of b sub I. And so we can break up summations over addition. Now this is basically just using the commutative property. Addition is commutative, so the order we add things up in doesn't really matter. So instead of adding like am to bm, we can just redistribute everything, add all the a's together, and then all the b's together, rather than mixing them like we're doing on the left. Third, we have the sum from I equals m to n of a sub I minus b sub I is equal to the sum from I equals m to n of a sub I minus the sum from I equals m to n of b sub I. So this is similar to the idea that we were just talking about a second ago, with how we can distribute, commute to group all the a's together. We can do basically the same thing here. We're just moving all of the a's to the front, adding all of them up, and then we're subtracting off all all of the b's that we were. So rather than subtracting them off after each a sub I, we're just going to subtract the sum of them all off at the end. Okay, and so these are the three main summation properties to be aware of. These give us an idea of how to compute summations a little bit faster, as we can break them apart. And so we're going to talk about how to do that in a second. So first we're going to talk about special kinds of summations now. So the first type we're going to talk about are what are called telescoping sums. Now what a telescoping sum is this is a summation where all but the first few, and few is a bit of an arbitrary term, but the first few terms and last few terms cancel out. Okay, so telescoping sum, all but the first few and last few terms cancel out. So we can simplify it dramatically. It kind of collapses in on itself. The name comes from the idea of a pilot's telescope. You can think of like you can collapse it in or expand it on itself just by pulling it in and out. That's kind of the idea, is that we will expand the whole thing out and then we're going to collapse it in on itself to get a small thing that we can compute. And so an example of this is if we look at the sum from I equals 1 to n of I to the fourth minus I minus 1 to the fourth. Now the hint of if you have a telescoping sum or not is if you have a difference of two things that are going to repeat the same values a lot. So like these only really differ by 1 and then we're taking it to the fourth power, that's a good sign it's telescoping. And if we write out some of the terms, this would be like 1 to the fourth minus 0 to the fourth, plus 2 to the fourth minus 1 to the fourth, plus 3 to the fourth minus 2 to the fourth, and so on, up to n to the fourth minus n minus 1 to the fourth. We're actually going to do one more term. N minus 1 to the fourth minus n minus 2 to the fourth, plus n to the fourth minus n minus 1 to the fourth. So I'm just writing out the summation, just expanding it like we talked about before with what it means. But notice things cancel out. This 1 to the fourth here cancels out with the negative 1 to the fourth in the next term. The 2 to the fourth here cancels out with the 2 to the fourth in the next term. The 3 to the fourth here will cancel out with something in the dot, dot, dot. It'll cancel out with the negative term in the next thing. And if we go to the end, the n minus 1 to the fourth here cancels out with the minus n minus 1 to the fourth that was in the next term. Now here we have n minus 2 to the fourth. But that'll cancel out with something in the previous term. And so you just have to kind of think through like what's gonna cancel. As they differed by 1, I and I minus 1, you should expect basically all but one thing to cancel. And that's what we see here, that one of the very first terms didn't cancel and one of the very last terms didn't cancel. And that was it. And so we're left with a negative 0 to the fourth from the first term and an n to the fourth from the last term. And those were the only things that didn't cancel, and so our sum becomes n to the fourth. Now we are going to see another very similar example of a telescoping sum in a second, but the thing to look for are two things that only are like differing by 1 into what you're plugging into the same function. So we're plugging both of these into the x to the fourth function, and then subtracting them, just shifting where we started. And that gives us the idea that we're going to have a telescoping sum. So now we want to get a few formulas for summations. So just formulas to make computing sums a lot easier for us. So our first formula is the sum from I equals 1 to n of 1. So this is literally just saying add 1 to itself n times. Well, as you learned, I assume in elementary school, If you add a number to itself repeatedly, that's the same as multiplying that number by it, the number of times you added it. So we're adding 1 to itself n times, so this is just n times 1, which is n. And so we know the sum from I equals 1 to n of 1 is just n, and using one of our multiplication properties, summation properties, the sum from I equals 1 to n of a constant is just n times that constant. Remember, we can just pull the constant out, do the sum of all the 1's, and then multiply. Or you can think of it as we're just adding c to itself n times, so we get n times c. So the next summation we want to compute is the sum from I equals 1 to n of I. So this is 1 plus 2 plus 3, and so on up to n. And we want to compute what this equals. So what we're going to do here is we're going to do a bit of a mathematical trick that was originally discovered by Carl Friedrich Gauss, who is a famous mathematician. So what we're going to do is we're going to let this whole thing equal s. So s equals 1 plus 2 plus 3, and so on up to n. And I'm just writing s for the summation because it's kind of shorter to write s. But now what if I added backwards? So I'm going to just add these terms up, but now in the opposite order. So instead of doing n at the end, I'm going to do it at the first. So I have n plus n minus 1 plus n minus 2, and so on to 1. So I'm still adding up the same terms. I'm just doing it backwards. And we talked about how addition is commutative, so I'm getting the same value. Now the mathematical trick here is we're going to add these two things together. So if we add the left-hand side together, we get 2 times s. We've just added the summation to itself. But now we're going to redistribute on the right side as we add. We're going to commute. So we're going to do 1 plus n. Well, that's n plus 1. Plus, we have 2 plus n minus 1. Well, that's also n plus 1. 3 plus n minus 2. Well, that's also n plus 1. And so on, with how we've lined things up, we're going to end with n plus 1, so we get n plus 1. So we're just going to get a bunch of copies of n plus 1. But we just talked about what happens when you add up something to itself repeatedly. It's just the number of times you added it to itself times that thing. And so how many times did we have n plus 1 to itself? Well, it's just the number of terms in the sum. And there are a total of n things in that sum, so this becomes n times n plus 1. Because we've added n plus 1 to itself n times. And now we wanted to know what s was. So s is just going to be equal to n times n plus 1 divided by 2. Just dividing by 2 both sides of the combination we just did. But remember, s was our summation. So what we just found is the sum from I equals 1 to n of I is equal to n times n plus 1 divided by 2. And so this gives us a formula to add up the first n natural numbers. Now, this is kind of an interesting trick. That's how we come up with a lot of formulas when it comes to summations, is we just think of adding it in one way, adding it in another way, and then combine things. And that's what we did here. We did it in the one way, which was literally just writing it down. Then we did it in the other way by just adding it backwards, and then we just combined the two. Okay, and now just to kind of reiterate what this formula is saying, if I wanted to compute the sum from I equals 1 to 100 of I, so this is just saying add the first 100 natural numbers together. So we're doing 1 plus 2 plus 3 plus 4 up to 100. Well, with our formula we just found, n is 100, so we just have 100 times 101 divided by 2, which is 50 times 101, so we get 5,050. And so we just added up the first 100 natural numbers very quickly. And so that's kind of the power of these formulas that we're going to be finding. They allow us to add things up at a very fast rate. And it's kind of a cool party trick to be able to tell someone that you can add up the first 100 natural numbers and then just tell them it's 5,050, that you can do that in your head. That's kind of a cool party trick if they don't know about this formula. So next we're going to look at a bit more complicated of a formula. We want to do the sum from I equals 1 to n of I squared. Now, you might be tempted to, which again, this is 1 squared plus 2 squared up to n squared, just to kind of refresh you, as we just barely defined sigma notation in this video. Now, you might be tempted to do some similar trick to what we just did, and so try to add things kind of in reverse order and combine things. The problem is that squaring doesn't really distribute over addition, and so trying to combine things that way doesn't work very nicely. And so what we're going to do is we're going to use our knowledge of sigma notation, of telescoping sums. And we're going to use kind of a trick with telescoping sums to do this. And I just want to note, this is not the only way to prove this. This is using the idea of telescoping sums that we just barely talked about, though. And so what we're going to do is we're going to look at the sum from I equals 1 to n of 1 plus I cubed minus I cubed. Now, this has the appearance of a telescoping sum, but I want to point out why this is actually the thing we're going to look at. And the reason for it is that if we actually were to simplify the expression on the inside, if we do 1 plus I cubed, we get 1 plus 3I plus 3I squared plus I cubed, and then minus I cubed. And so this is the sum from I equals 1 to n of 1 plus 3I plus 3I squared, and then the I cubes cancel. And using our properties from before, this becomes the sum from I equals 1 to n of 1 plus 3 times the sum from I equals 1 to n of I plus 3 times the sum from I equals 1 to n of I squared. But we know how to compute two of these. The sum from I equals 1 to n of 1 is just n, and we computed this sum a second ago. This is just 3 times n plus 1 divided by 2. And this is 3 times the thing we want to compute. And so because of that, we're just going to write this as 3 times s, where s again is the thing, the summation we're trying to compute. It's this sum up here of I equals 1 to n of I squared. And so this means we've really just got a sum of 3 things, one of them being s, and the other being things we already know. But we can compute this summation also using telescoping sums. And so this is another trick in mathematics, is we added it in one way, namely in this way we just barely did. Now we're going to add it in another way, and they have to be equal because we're adding in 2 different ways. And so now we're going to do a telescoping trick sum. And so, like I said, this is a telescoping sum, so if we add things up, we can see what cancels. So we're going to have 2 cubed minus 1 cubed plus 3 cubed minus 2 cubed, and so on up to n cubed minus n minus 1 cubed, and we're ending with n plus 1 cubed minus n cubed. Now, I don't think I mentioned how to know where you stop with a telescoping sum before, but it's just coming from this top thing. So I stop when I plug n in, and so on this last term I've plugged n in, so that's why I know I've stopped. Because if I plug n into 1 plus I get 1 plus n cubed. Now looking for cancelizations, we have a 2 cubed here that cancels the 2 cubed in the next term. Our 3 cubed will cancel with something in the dot dot dot. The n minus 1 cubed here cancels with the nothing. Never mind. Well, it cancels with something in the dot dot dot. The previous term is going to have a n minus 1 cubed in it in the positive. And this n cubed cancels with this n cubed. And so we are left with basically the first and last terms. Now, because 1 plus I and I differ by 1, that's expected. We expected that we'd only have the first and the last terms left. just 1 from each. And so we're left with a minus 1 cubed here, and we're left with an n plus 1 cubed at the end. And so now, just actually doing this is going to be n cubed plus 3n squared plus 3n plus 1 minus 1. So we get n cubed plus 3n squared plus 3n. And so that is our summation. But it must be equal to the other thing we just computed above. So our two sums that we just computed must be equal to each other. And so we're going to set them equal to each other. And so we've got n cubed plus 3n squared plus 3n needs to equal 3 times s, the sum we care about, plus 3 times n plus 1 divided by 2 plus n. Now we're going to actually multiply out this side, so we get 3s plus 3 halves n squared plus 5 over 2n. So I'm just distributing the 3n across here to both terms, and so I get a 3n squared divided by 2, which is the 3 over 2n squared. And then I get a 3n over 2 plus another n, so that gives me the 5 over 2n. Just getting a common denominator there. So now we want to solve for s, and so we're going to get everything on this right-hand side, move it over to the left. So we get 3s equals, and then I'm just going to subtract off the 3n squared, 3 halves n squared, and the 5 halves n. And so I'm going to have n cubed plus 3n squared minus 3 halves n squared plus 3n minus 5 over 2n. And so this becomes n cubed plus 3 halves n squared plus 1 half n. And now we just want to simplify this a bit. And so this is going to become, getting a common denominator of 2, we get 2n cubed plus 3n squared plus n, all divided by 2. But that's 3 times s, so I'm going to divide everything by 3. And so we get s equals 2n cubed plus 3n squared plus n divided by 6. And you can factor the top if you want as n times n plus 1 times 2n plus 1 divided by 6. And so that is our summation of all of the perfect squares from I equals 1 to n. So we found the sum from I equals 1 to n of I squared is n times n plus 1 times 2n plus 1 divided by 6. And so this gives us a shortcut to add up the first n perfect squares. Admittedly, this formula is more complicated, but we were able to compute it all the same. Now let's summarize what we've done with these formulas. And so we found the following formulas. The sum from I equals 1 to n of 1 is n. The sum from I equals 1 to n of I is n times n plus 1 divided by 2. The sum from I equals 1 to n of I squared is n times n plus 1 times 2n plus 1 divided by 6. And we haven't computed it, but I'm just going to write down the I cubed one. The sum from I equals 1 to n of I cubed is n times n plus 1 over 2, all squared. And you can compute this using a telescoping sum, just like what we did above. So the method that we use to compute I squared also works for I to the fourth. You just look at, would also work for I cubed. You just look at 1 plus I to the fourth minus I to the fourth. That'd be your telescoping sum. Compute it in the two different ways, set them equal, and you can compute this. And we can go higher, but that's as high as we're going to worry about going. You never go past I cubed really in a Calculus 1 class. But the benefit of this is using these formulas, we can now compute more complicated summations. And so suppose we want to evaluate sum from I equals 1 to n of I times 4i squared minus 3. So I want to compute this sum. This would be pretty hard to do without the formulas that we've just talked about. But using our formulas, we know we can rewrite this as the sum from I equals 1 to n. Now we can't pull the I out because it's not a constant, but we can multiply it in to get 4i cubed minus 3i. And now we can break up over a subtraction to get the sum from I equals 1 to n of 4i cubed minus the sum from I equals 1 to n of 3i. We can pull constants out to get 4 times the sum from I equals 1 to n of I cubed minus 3 times the sum from I equals 1 to n of I. And now we're just going to use our formulas. We know how to do the sum of I cubed. I told you what it was. And we computed the sum of I earlier. And so using our formulas, this is 4 times n plus 1 over 2 all squared minus 3 times the sum of n times n plus 1 over 2. Now multiplying this out, we're going to get n squared times n plus 1 squared divided by 4 times that, minus 3n times n plus 1 over 2. So we've got n squared times n plus 1 squared minus 3n over n, I'll multiply that out, times n squared, 3n squared plus 3n over 2. This then becomes n squared times n squared plus 2n plus 1 minus 3n squared minus 3n. Oh, I'll write it this way still. Minus 3n squared plus 3n over 2. Now we want to get a common denominator. So we're going to have to multiply the first thing by 2 to get a common denominator of 2. So we're going to have 2n to the 4th plus 4n cubed plus 2n squared. Multiplying that out and multiplying by 2, minus 3n squared minus 3n, distributing the negative like I tried to do a second ago, all divided by 2. And this becomes, canceling things out, we get 2n to the 4th plus 4n cubed. We've got 2n squared minus 3n squared, so we get minus n squared minus 3n divided by 2. And so we were able to compute the summation. Now you might wonder, why would I ever want to compute a summation like this? And the answer is, in the next unit, we're going to talk about summations very much like this. And being able to compute them is very helpful. Now we're going to look at an example that is kind of where we're going to be using this. So this example is kind of where sigma notation really shows up in Calculus 1, is computing sums like the following. And now the reason why we'll compute sums like this will make sense after the next video. But for now, we're just going to practice doing it. So now what we want to do is the following. We want to compute the limit as n goes to infinity of the sum from I equals 1 to n of 3 over n times I over n cubed plus 1. And so we want to compute this limit of a sum. Now, this would be almost impossible if we couldn't first compute the summation. And so we're going to use all of the knowledge of what we've talked about with these formulas to compute the summation, and then we'll just have to compute the limit after the fact. And so to start with, we could pull the 3 over n out of the summation, and in fact, that would be totally fine. Or we can leave it in. I'm going to leave it in for a moment, just because I'm going to multiply things out. So if the limit is n goes to infinity of the sum from I equals 1 to n of, I'm going to just leave the 3 over n alone for a second. I've got I cubed over n cubed plus 1 And now if I multiply my 3 over n in, I have the limit. So n goes to infinity of the sum from I equals 1 to n of 3i cubed over n to the 4th plus 3 over n. Now I want to break the sum up. And remember, you can break limits up as well, but we're not going to worry about that. So if the limit is n goes to infinity of this whole thing, so we have the sum from I equals 1 to n of 3i cubed over 4n to the 4th, plus the sum from I equals 1 to n of 3 over n. Now we want to factor out our constants. This is the limit as n goes to infinity. Now, n is a constant in this case until we do the limit. So n is some fixed value until we actually apply the limit. So it can be factored out. So we get 3 over n to the 4th times the sum from I equals 1 to n of I cubed plus 3 over n times the sum from I equals 1 to n of 1. Like I said before, we could have pulled the 3 over n out of the summation to start with, and then just multiplied it in at the end before we did the limit. It would give you the same answer. This is just one way of doing it. But now we know how to compute each of these sums, and so that's what we're going to do. So we have the limit as n goes to infinity of 3 over n to the 4th times the sum of I cubed from I equals 1 to n as n times n plus 1 over 2 all squared plus 3 over n times the sum of just 1, which is n. We've done that before. And now we want to simplify this expression. And so simplifying this expression, we have the following. The limit as n goes to infinity of 3 over n to the 4th. And now multiplying this out, we're going to get n squared times n plus 1 squared over 2 plus 3 at the end. And so this is the limit as n goes to infinity of 3 over n to the 4th. And now I'm going to multiply the top out. So I'm going to get n squared times n squared plus 2n plus 1 all over 4. That should be a 4, not a 2. Plus 3 at the end. So this is the limit as n goes to infinity of, now we're going to multiply stuff out more, so we get 3 n to the 4th plus 3 times n squared times 2n, so we're going to get 6 n cubed plus 3n squared, all divided by 4n to the 4th plus 3. Now, doing the division here, we have 3n to the 4th divided by 4n to the 4th, so that'll just give us 3/4, plus 6 over 4n, plus 3 over n squared, plus 3. So I'm just dividing each term here. We've done this type of limit before, so I'm just dividing each term separately by the 4n squared. And so that's how I got to that. Now as we take the limit as n goes to infinity, we know that 1 over n goes to 0. So 6 over 4n will go to 0, and 3 over n squared goes to 0. And so we get 3/4 plus 3. And so this is 3/4 plus 12/4. So we end up with 15/4. And so we were able to compute this whole summation as being equal to 15 over 4. And we wouldn't have been able to do that if we didn't know how to compute these summations using these formulas that we've mentioned. But we were able to do so using these formulas.